Good day everyone, we are the Group 3. I am Manguiat Rose and together with my members Macaraig Jimwel, Maruquez David, and Mondelo James, presenting our project titled Simulation of Boot Multiplier in Xilinx Vivado. We are going to present the following: Introduction, Block Diagram, Verilog Codes, Schematic Design, Results and Discussion, and Conclusion.
Good day, sir. I am James D. Mondelo and I'm going to discuss the introduction of our paper. So the boot algorithm is a multiplication algorithm that can multiply the two signed binary integers. It is also used to speed up the multiplication process and it's very effective. It operates on a string of zeros in the multiplier that only shifts the rightmost string of bits, a string of ones in a multiplier bit weight of 2 raised to k to 8 2 raised to m, which can be thought of as 2 raised to k plus 1 minus 2 raised to m. Andrew Donald Booth developed the algorithm in 1950 while working on crystallography research in Birkbeck College in Bloomsbury, London. The ability of this algorithm to handle both positive and negative multipliers equally is helpful. When the multiplier contains a few significant block of ones, it is more effective regarding the number of additions required. The data determines how much speed can be gained by skipping one of digits. Furthermore, using this method requires fewer additions and subtractions. Also, the boot algorithm generally requires examining the multiplier bits and shifting the partial product as long as the following guidelines are followed. The multiplicand can be added to the partial product, subtracted from the partial product, or left unchanged before shifting. And the multiplicand is first subtracted from the partial product when the multiplier encounters the first least significant one in a series of 1. When the multiplicand encounters the first zero in a string of zeros in the multiplier, it is added to the partial product or providing there was a previous one. And finally, the partial product remains unchanged when the multiplier is the same as before. And for the application, the boot multiplier algorithm employs addition and shifting. It is also function as an arithmetic operator in a digital signal processing or DSP and Fourier transform and filtering applications. It is also used to achieve high execution speed. These multipliers consume most of the power used in DSP computations. Also, DSP is used primarily in areas of the audio signal, speech processing, radar, seismology, audio, sonar, voice recognition, and some financial signals. For example, DSP is used for speech compression for mobile phones as well as speech transmission for mobile phones.
Good day, sir. I am Jimwel, and I will be discussing the flowchart and block diagram. This figure shows the flowchart for implementing the boot multiplier. Initially, we have multiplicand M, multiplier Q, our product A, our 1-bit register Q1, a conditional statement is applied for the values of Q0 and Q1. Q0 is the least significant of the multiplier, and Q1 is the assigned bit of 1-bit register. For the case that the value of Q0 and Q1 is at 1 and 0 respectively, the multiplicand is subtracted to the partial product. On the other hand, for 0, 1 value, the multiplicand is added to the partial product. The arithmetic right shift will be performed. For those, the case that the values of Q0 and Q1 is equal, whether it is 1, 1 or 0, 0, arithmetic right shift is also implemented, but no addition or subtraction will be performed. At this point, when the right shift is done, the count value will be reduced by 1, and checks whether the count value is equal to 0. When the count value is finally 0, the program will end and we will get our final answer. For the block diagram, it shows the block diagram at the top module of the boot multiplier when implemented in a 7-segment display. This presents block of boot multiplier, clock divider, refresh counter, anode control, BCD control, and 7-segment controller.
And then we have here the Nexus 4 RTX 7 FPGA board. The Nexus A7 is a user-friendly yet powerful FPGA development board. It is a ready-to-use digital circuit development platform based on a Xilinx RTX 7 FPGA family that brings industry applications into the classroom. The Nexus 4 DDR, with its large, high-capacity FPGA and collection of USB, Ethernet, and other ports can host design ranging from a simple combinational circuits to powerful embedded processors. The following are the sum of the board's features: 128 MB DDR2, serial flash, built-in USB UART for downloading image and chip scope debugging, micro SD card reader, and 16 switches and LEDs.
For the input switches, Table 1 shows the equivalent values of positive decimals in binary, while Table 2 shows the equivalent values of negative decimals in binary. Since the boot multiplier is a 4-bit input program, the maximum value that we can input is up to 15, which is 1111 in binary. For the negative sign decimals, they should first be converted into their corresponding 2's complement, as shown in Table 2. Now the value of negative 15 in binary is 10001. The picture on the left shows the 7-segment part and the switches that will be utilized if this boot multiplier will be implemented on board. There will be a total of 4 7 segments that will be used. This is for the sign bit. Y1 is the MSB or the most significant bit of the product, while Y3 is the least significant bit. And this will be the switches that will be used for the inputs. We will now move on to the Verilog codes. The figure shows the main module of the boot multiplier built using a behavioral model of level of abstraction. The B and Q have 5 bits input binary representing multiplicand and multiplier respectively. Z is the 2's complement output, while P is the hex output. The for loop will continue until it reaches the number of bits of the inputs. In this system, since the inputs P and Q are 5 bits, the for loop will continue from 0 until 4. The case statements follow the flowchart of the boot multiplier. After the loop, the right shifting of all variables Q and Z will be performed, and the loop will continue until the last number of bits. The Qi will be the new Q1 for the next loop. The if-it statement, if Z9 is equals to 1, means that the output is negative. Thus, the output should be converted into its hex value through negation of Z plus 1. But if not, the P will just copy the Z. The P is now the hex value output. This P will be then converted into binary coded decimal using hex BCD given in the next slide. Different values of B and Q were set as shown in this figure to test whether the program will return the correct sign and product for each state. After converting the 2's complement output to hex in the boot multiplier module, the hex value should be converted into the binary code decimal for the 7-segment implementation on FPGA board as shown in hex to BCD conversion module. Since the output P is a hex value is 10-bit, the for loop will continue from 0 to 9 bits until the bits are all converted. On the other hand, the sign bit will be based on Z9, where if Z9 is 1, the sign bit will be set to 15 or 4B1111 or F, which means the output is negative. When the Z9 is 0, the output is positive, setting the sign bit to 14 or E or 4B1110. These are crucial for the 7-segment implementation of the negative sign display. The outputs are divided into 4 bits, thus the program has Y1, Y2, and Y3 in 4 bits as outputs.
The figure above shown on the screen is the clock divider and the refresh counter module. The refresh counter and the clock divider modules are necessary to determine and have a perfect timing for the 7-segment displays. Recalling on what we have learned, especially in the microtrack, the clock divider is used to divide the clock frequency so that when it is implemented on the board, the change in the output is not so fast. However, the refresh counter is used to have a timing on the output so that the output in the 7-segment display is accurate. So as we can see here in the first figure is the clock divider module in which it's used the command input designate the clock as input and the command output to designate the end clock as output. However, in the refresh counter module, we can see here also the command input and output, and then in the input, it's used the R clock, and then in the output, it's used the R counter.
For the anode control module, it pertains to the anodes on the FPGA board. Since the implementation of the project only uses 4 7-segments, there are also 4 case statements as shown in this figure. In addition, the BCD module controls the number that will be displayed on a certain anode. The refresh counter and clock divider enable both modules in order to simultaneously display the different outputs in the 4 7 segments in Figure 10. The module of the 7 segment will not display any non-decimal values as indicated by the case statement. The 15 case was added to display the negative sign of the sign bit. If z of 9 is 1, the output reg sign bit will set to 15 or 1111 in 4 binary digits. The segment will then be set to 7 binary 011111, only turning on the middle of the segment for the 7 segment display. On the other hand, if z of 9 is 0, indicating that the output is positive, the 7 segments will be turned off.
Good day everyone, good day sir. I am David Maruquez, one of the members of Group 3, and I will be presenting today the main and top module with its test bench, the XDC file, this schematic diagram, and the simulation result. But first, let's discuss the main module, top module, and test bench. The main module is the architecture of the design, and here we instantiated the important blocks including the boot multiplier, the clock divider, the refresh counter, anode control, BCD control, and 7 segment controller. So the boot multiplier is the most important block because the main purpose of our design is to multiply two sign bit numbers. Next, clock divider will reduce the clock frequency of the board from 100 MHz to 10 Hz to make the output observable in the board. Next, refresh counter was implemented to have perfect timing for the 7 segment display. Anode control will control which of the 8 7 segment display on the board will operate. BCD control will control the number that will be displayed on the 7 segment display. The input of this main module is R switch 1, which is 5-bit, which is equivalent to 5 switches in the board, and switch 2, which is also 5-bit, and which is also equivalent to 5 switches also. The output is connected to the anode and 7 segment control for displaying output in 7 segment display. In the test bench, this will make us have a simulation result in Vivado, and random inputs were used. Then the top module has inputs and outputs that were based on the XDC file that I will discuss next. So let's proceed to the next slide. But first, I will explain the XDC file. So the format for XDC file or code were obtained on the internet on the site of Xilinx. There are many master XDC file. There are many master XDC file there, but we chose master XDC file for Nexus 4 RTX 7 FPGA board. So here on this slide, we uncomment DCLK or clock because boot multiplier uses a clock, and this circuit is a sequential circuit. So next slide. This is also part of the XDC file. Here, it shows that all 10 switches on the XDC file were uncommented and were used. Switch 0 to switch 4 is for the first 5-bit input, and the switches 5 to 9 is for the second 5-bit input. All the inputs were based on the inputs used in the top module that we have discussed earlier. Next slide. So this is also a part of XDC file, but here it shows the 7 segment display part. So since we need all the 7 segments on the 7 segment display, so we uncommented all of it and changed the input name based on the top module also. Next, on this part, we uncommented all the anodes because on the anode control, On the anode control module that was discussed earlier, we use all the anodes in the board. So that's all for the XDC file. Let's proceed to the schematic diagram of our design. As you can see, our top module for the design matches the resulting schematic diagram in the Vivado, which means that the architecture of the code has no problem. This presents block for boot multiplier, clock divider, refresh counter, anode control, BCD control, and 7-segment controller. This design aims to display the product of two 4-bit inputs B and Q to a 7-segment display. Switches 1 and switches 2. I mean, there are two 4 bits, but they have extra 1 bit, which is the sign bit. So, switches S1, SW1, and SW2 with 5 switches each are for the multiplicand B and multiplier Q respectively. 4-bit input boot multiplier has outputs of a sign bit Y3, Y2, and Y1 which are derived from the hex to BCD module. These outputs are the input of the BCD control to have binary coded decimals to be displayed and to pass a corresponding digit in a 7-segment display. The clock is a 100 MHz, which we mentioned earlier. So 100 MHz clock input to a clock divider module. Clock divider module is connected to refresh counter which then counts from 0 to 3 and acts as the input to the BCD control and anode control. Refresh counter enables the module to choose which anode will be turned on and which digit will be displayed at the same time. The output in the 7-segment controller is a 7-bit cathode and in anode control is the 8-bit anode. Let's proceed to the RTL analysis. So the first two figures shows the boot multiplier with B and Q on the left image as the inputs, and on the left side, it is the implementation using switches with clock, and the figure below shows the schematic diagram of the program as well as the expanded view of the boot multiplier using different combinational and sequential gates. So lastly, for my presentation, so upon simulating the main module together with the test bench, we have obtained the behavioral simulation or the simulation result. It shows that the boot multiplier we have designed operates accurately. The F, as you can see on the screen, corresponds to the negative sign, while the E is the positive sign. The Y1, so Y1 is the MSB or most significant bit, while the Y3 is the least significant bit of the decimal products. For 15 times 15, the system was able to return a 225 or 225 as indicated by sign bit equals E, which is positive, Y1 is equals to 2, Y1 is equals to 2, and Y3 is equals to 5. So that's all for my presentation. Thank you very much, and let's proceed to the next presenter.
The device implementation of the boot multiplier was also obtained in Xilinx Vivado. The total on-chip power is 0.136 watts, where there is 28% dynamic power of 0.39 watts and 72% static of 0.097 watts. On the other hand, the junction temperature is 25.6 degrees Celsius. The system has also used 246 LUTs as shown in this figure.
This is the simulation of boot multiplier in Xilinx Vivado. This is the main module of the boot multiplier, the test bench, the hex to BCD module for the sign bit, the clock divider module, the refresh counter module, the anode control module, the BCD control module, the 7-segment module, the main module, the test bench, and the top module. This top module should be set as top as shown in this menu. We will now run the simulation. This figures the behavioral simulation of the boot multiplier. We can observe that the P and Q are in their hexadecimal value. That's why we will just change the radix into signed decimal, as shown in this demo. Now the B is in its original signed decimal as well as the Q. Negative 15 times negative 15 should produce a product of negative 225. Remember that F is negative, while E is positive. Thus, this behavioral simulation indicates that the boot multiplier works properly. We will now run the RTL schematic. This is the block diagram of the main module, where the switches 1 and 2 are the inputs and the outputs are the anode or the 7-segment. We can expand this block diagram. And now, we can see the individual modules such as the clock divide, refresh counter, anode control, boot multiplier, BCD control, and the 7-segment. We can also expand this boot multiplier, and now we can see other combinational and sequential logic gates that was used for the implementation of the boot multiplier in the RTL analysis. Now we will move on in running the synthesis for the device implementation. Now the synthesis is complete. Running the implementation, we can now view the device implementation. This is the device implementation, while this is the timing analysis. This is the power analysis. The design runs with 246 LUTs. And now we can generate the bit stream. This bit string will be used for the implementation of boot multiplier on Nexus 4 Arctic 7 FPGA board. And that's all for the simulation in Xilinx Vivado.
In conclusion, the boot multiplier simulation using Xilinx Vivado is done. This project might also be done on the Nexus 4 Arctic 7 FPGA board and 7-segment display. But, unfortunately, the students don't have the actual board. Boot multiplication algorithm is designed in 2's complement multiplication algorithm that multiplies two signed binary digits in an efficient way. B is the multiplicand and Q is the multiplier. Take in consideration that the multiplier is only for 4-bit input. Inputs for representation of the switches are done as negative signed decimal values should be in 2's complement. Boot multiplier output is displayed in 7-segment display. The total on-chip power is 0.136 watts and it uses 246 LUTs. The behavioral simulation, RTL schematic, synthesis, and onboard simulation were also done for the project. That would be all and thank you. To meet our team, this is me, this is Mary Rose, this is David, and this is James. Thank you all for listening.